Okay, can you see my screen?
Yeah.
So it should show the Chainweb client APIs picture. And so there's a mempool, and the mempool is I put it into Puck because it's not really service API. They're pretty tightly coupled currently. Kind of mempool has a callback into Puck service, and it's also per chain. So I put it in there. One thing why I draw it at all, which becomes important later, is this is P2P thing there in the corner, which is essentially everything where nodes communicate with each other. Clients shouldn't see it. There's a whole API kind of related that is only for node-to-node communication. And this P2P thing is essentially node-to-node communication. So it's something over the network, but clients shouldn't care about.
And that P2P stuff happens on the level of a per chain level?
Yes. For the mempool, it's per chain. And that's why mempool makes it expensive. And that's important when we make decisions in the future about, for example, we have to be really careful that P2P for the mempool is not killing other, because it's very easy. You make a small change there and it kind of, everything you do there multiply by 10. That's what the actual resource consumption is. And it's very easy to take away resources from consensus. That's one reason why I put it here, so that people are aware this thing interferes. Essentially, it races for resources with consensus. Okay, so this is kind of everything without consensus, essentially. Well, the question is, okay, if you want to now, if you look at this picture, you ask yourself, where are the blocks stored? Mining coordinator calls new block. This DB and Puck is really just a Puck DB. It's kind of application level DB. It's not the chain DB where we have blocks and payloads. So where do we store it? And an obvious solution would be, let's store it. It's kind of every chain has its own database. Let's put it into per chain. And that's actually what we implemented when we started implementing everything. So it looked like this picture. You see this chain data there. It's essentially the payloads and the block headers. And there per chain, if we have in the code, you find something that is called tree DB and block header DB. This is exactly, plus the payloads. This is essentially this thing here. We put it into it was not in Puck service. Well, it's here not in Puck service, but it was per chain. And so we did that. That was our very first plan. And the reason behind it was that we had the idea we first implement a single blockchain. And when we have the single chain thing, then we kind of create more chains and we connect them and kind of build a web. Kind of this idea, we first do one thing and then we braid them together. We copy it and braid it together. And this was what we implemented. And it looked a bit like this. And and I show it to you really only because a lot of stuff in the code kind of still reflects this early approach. And so the next question is, okay, so we have that. So one thing I forgot on this picture, the chain data box should have a small thing called P2P in there. I was too late preparing the slides or this picture. So think of you see my cursor?
Yeah.
Yeah. So there should be a small corner saying P2P2. Because the chain data is a thing that has to be synchronized, and this would essentially be consensus. And we actually implemented it like this initially. And now you can say, hey, wait, the chains are not completely independent. They need some sort of braiding. And so this we implemented then. So then we had one chain, it worked fine. So now we multiplied the chains. And then we implemented a small box, this validate braiding thing. It was a function that the mining coordinator, or at that time it was called just mining, would call. And that also the chain data, when we put something in the database, we would just call and say, hey, can you check that this blocks that we just put in the database is correctly braided? So the implementation looked like that. And it was just a call you would do. And so the braiding thing would actually call back into the chains and look if everything was all right. And then we ran it. And this was actually the picture that I'd show you now was not on the real system, but a simulator that we built in the very early days. And what happened was kind of, let's start here. Kind of the thing worked really nice. You see, kind of we built a chain. Kind of there are several chains running parallel, nicely braided. And at some point, something that you see at the top happened. Most of you have seen these pictures, but I'm not sure if everyone knows about them. So that was a very interesting lesson. So you see that the chain stopped here, and there was this explosion of many, many blocks that were weirdly connected. If you zoom in, can we do that? You see that there's I have a picture that zooms in right below. you see, this is kind of how it looks at the top. And the question is, what happens there? There are many blocks at the same height. And essentially, how it happened was there were 1 or 2 orphans in the chain. And then the whole thing exploded. We got tons of orphans and the whole thing stopped. And all nodes were running at very high CPU trying to find a valid braiding. And what happened was they couldn't mine a new block and verify that it was correctly braided over all chains. So this was happened here. And if you had more chains in there, we did simulations with 1,000 chains or so, things blew up in a terrible way. And even here, it took me sometimes hours to figure out what was the conflict in here that prevented us, that deadlocked the whole thing. So that was a little bit of a bummer, but this approach that we implemented here didn't work because nodes got stuck because they could validate the braiding, but they could not find, if something got a little complex, they couldn't find valid braidings. So, what we did next, and this was essentially the first real Chainweb implementation looked like this. We implemented consensus on Chainweb level, not on the chain level. So I told you before, in this picture, we had this chain data and it should have this P2P box in here in the chain data. And essentially consensus was done on a pair chain level. Every chain would talk to its peers and would find the longest branch. We dropped that and instead implemented consensus on a Chainweb level. And now what nodes were sent, they would not talk about the longest branch. They would talk about the longest web that they had. And if you have a single chain, essentially the head of a chain is a single block header. If you have a web, the question is what is the head of the chain, and this is what we call a cut. The name cut comes from I think it's used in semantics of Petri nets and concurrent computations. It's a notion that happens. It's used in other fields in computer science for if you have a concurrent distributed computation, often you call kind of this distributed state a cut. So, and this is what happens here. Essentially, we compute several chains in parallel, but they have to synchronize in some way. And that's what we call. Therefore, we choose the same name because it's actually the same kind. And, okay. So in the code, now you see essentially we had implemented in the first versions, and we still have it kind of the chain data is, for every chain, we have one database essentially that we call block header database. And it's an instance of TreeDB. And we can look at the code if you want later. So what we did then, we fixed the thing by essentially taking a block header DB and appending the name web to it in the code. I highlighted it here. So if you see something in the code that starts with web and then something like web block header DB, or there's a web packed service, I think, and there are several things with a web in front. It's essentially, we just slammed kind of the per chain implementations that we had. We slammed them together and put them in one component. And you see that in the code. The important thing is these components can't be really used anymore individually. Well, you can run a single Chainweb, but if you want to run a Chainweb, you really have to talk about cuts. And it was not only that we needed cuts, we needed an algorithm to efficiently find the next cut, because this was the thing that deadlocked the whole Chainweb when we didn't have it. So this is what we implemented, and it looks like this now. And I'm really, can I flip it here still? Turn it around? Oh, here it works, but you can't see the whole thing. Can I?
If you open this in another browser, it might do the auto flipping. In Firefox, it's auto flipping for me.
Ah, that's good. Yeah, I uploaded the picture in the right way. It's just that somehow in the Markdown it does not update it. Let's see if I can put it in here. I don't know how to upload the whole picture. Anyways, I go back here. You just have to turn your head a little. So what you see here, we implemented the consensus as an independent component. And now the P2P that was in the database that was up here in the chain, now the P2P box moved onto the Chainweb level. And that's actually quite good because it also reduces a lot of network overhead. And what nodes now communicate about is not individual block headers, but they share their current cut. And actually, they only share when they share the cut, they only share the cut hashes. So they only share the block hashes of essentially a cut is for every chain, the one block from each chain that have a correct braiding, that are close to the head of the chain. They're not necessarily the longest chain for each chain, but they are across all chains. It's the furthest we can get while still maintaining a braiding. And what we communicate is on the peer-to-peer network is only the, at least on the push level, kind of where we push stuff around, it's only the hashes of the block headers. And then each node will give that to the per chain level, and then the chains will kind of collect the actual block header and the actual data. But the communication, essentially, what is the current state, what is the consensus, is done on this Chainweb level. And in the consensus, we have the chain data, and I will go into more detail. This is kind of these components. So the chain data is essentially everything: block headers, payloads, and for all chains. Then we have something that is the cut, and I on purpose draw this database very, very small because
Lars, I just slacked you the rotated image.
Ah, cool.
It's in our private.
Okay, cool. Can you see it?
Yep.
Okay, so the cut, I draw it very small here. If we call it a database, we actually persist it, but we actually persist all the cuts, but when you can't really query it, it's really just one cut. It's the current consensus. So this small box here is when you read database in the code, it's really just one cut, and you can subscribe to it. You can always kind of get a stream of the newest cut. It's not necessarily cuts don't give you might skip some because there's no real notion of, there's an order, but it's only a partial order. So there might be some cuts that you don't see because they overlap in weird ways, but you always can get from this cutDB, it's really just storing one cut. Actually the hashes of one cut. And then we have this validation thing here, and we can go into detail there in a minute. And then we have a pipeline. It's essentially the same way as the Pact API or the Pact service communicates via a request pipeline. We have here a cut pipeline. So every new cut that comes in, you have to throw it into this pipeline. Then it goes through validation. Then we store it. And then we collect all data from it, and then we store it in the cut. So so the rough flow is really, a cut comes in, and every cut, even that if the local miner gets a new cut, it can read, or other components can read from this chain data, but they must never write to it. So every data that comes in has to go through this pipeline, kind of as a proposed new cut. It goes into validation. Validation goes to chain data, looks what is missing. If something is missing, it goes to P2P. It pulls everything tries to find in the network everything that is missing for that cut. Usually that's not a lot. So in most cases, it's actually the cut contains everything that is needed. So it's not used. So if something is missing, it goes to P2P. Then validation kind of finishes with it and then writes a new cut. And the new cut is posted, and the mining coordinator, for example, subscribes to it and then sees, oh, there's a new cut. The same way, if Pact service does some validation and it needs to validate payloads, it will go and read from the payload DB. And since validate block is only called on blocks that are already validated, everything that is missing, or all things that the block depends on, should at that point be in the database, because otherwise we could not have validated it.
Lars, is a cut, I can't figure out if a cut is partial or if a cut is not necessarily at the same chain height.
A cut, let's skip this. Can we kind of post because we can draw a cut. I can draw it on the whiteboard to give you an idea how they look. I will go into that in a minute. So this is a rough overview what is currently implemented, and in the implementation, if you zoom into these boxes, you will still sometimes find this per chain implementations, for example, for block header DB and things like this. And and this is more probably for Emily, the first thing, it's for people who want to do a deeper dive, and I'm very happy to just ping me privately, and we can talk about this because it's really exciting, or if you have to dive deep into the code. So one thing about the cut that is important is it allows us to inductively maintain valid bradings. And inductively means really in the sense of induction as you learn it in mathematics. Essentially, we want to keep an invariant in our code base that everything that is in the block header database has to be valid. The whole database has to kind of be this Merkle tree where everything is kind of consistent. But we don't want to go kind of validate the whole thing all over again. So if we get a new block, we don't want to have to validate the braiding all the way back to the Genesis block. So we need something where we only look kind of, we show for the last step, the new block, that something is valid. So essentially, validation always works like give me the header as a parent, give me the current header. Then I prove that assuming that the parent header was valid, the current header is valid. And we prove that for the Genesis block, that it's valid. And then we prove it for every step, essentially. And that way we should have proven that the whole thing is valid. And the problem with our first implementation is that we were not doing something similar, or we were not having a real inductive approach to the braiding. And cuts allow us to do this inductively. That when we have something that was a cut before, and we put a new cut on top of it, we know that the braiding is correct without going back too far in the history or by kind of searching through the history. And so this inductive thing is important. And there are a few more details. This was a little kind of sketchy what I just said. So a few more details to it. But it's, yeah, if someone is interested, I can go into details there. And the other thing is that it's distributed. So that and this was another problem with the first approach. Actually, each node was still trying to do its own braiding and check, and then it would just kind of the chains would sync, but the nodes wouldn't tell each other what their cut was. So every node had a cut. Every node knew that the blocks they had a valid braiding, but then they would just throw the blocks on the per chain level to other nodes, and the nodes would have to rediscover how this particular blocks that they got, the longest chain, would fit into some braiding. As essentially they would have to find their own cut. And that was the thing that was terribly, I think it's NP hard in worst case. And I think I proved that. So in order to prevent that, we now nodes have to tell each other complete cuts. It's not enough to just give you a block and say, hey, this is my longest block. You have to tell me how this block fits with other chains. And so this algorithm is so this means we can maintain the whole thing in a distributed way. And the important thing is that, again, I just throw these words out here. So some people, I'm pretty sure, know what it means. If you don't know it, it's not bad. But kind of there's a lattice of cuts, this allows us to implement something that's called eventual consistency when we store it. So that essentially means that everyone can compute cuts, but in the end we converge, but in a way that essentially when nodes synchronize, they converge towards having a common cut, which is essentially the precondition for having consensus. So everyone has their own idea what the reality is, but we can kind of merge our views into something that makes progress and always kind of gets us one step further without getting stuck. So these two properties, and these are actually theory properties. This is implemented in a module that is called cut, chainweb.cut. There are it needs, to make it really nice, it needs more work. The current implementation that we have there is not optimal. Kind of the way how we merge cuts, the way how the lattices work. It couldn't, if someone likes this part of theory stuff, take a look. And this is something, if we ever have time for that, it would be fun to write papers about it and come up with a really nice implementation and clean all this up and make it kind of, right now there's a little bit of mess in there. I try to put a lot of documentation. If you look at the model, chainweb.cut, I try to be very precise in documenting it. There might be, but the other thing is, if you change anything there, be very, very careful. We have essentially two implementations in there for merging cuts. One is correct, but very expensive. But it's simple. Correct are both. One, it's simple and just kind of tries to specify the property in simple terms that we can easily check it. But it's inefficient. And there's one that is efficient, but might be a little harder to understand. And in tests, we try to make sure that both are giving us the same results. And okay, so this is where my slides end, or my pictures. So I hope you have a rough overview kind of how the architecture of consensus. And by the way, we should update, I think, the architecture diagram on the README of the Chainweb repository, because what is there is terribly, it looks nice colors, but it's terribly outdated.
Lars, do we store every single cut ever received in the DB?
Yes, we do, but we
define DB though.
In the cut DB.
The cut DB.
The cut DB is a single pointer, right?
No, well, that's what we expose. Actually, internally, we store all, not the cut hashes, essentially. So it's a list of hashes, one hash for each chain. We store them all. Currently, it seems to be not to be a lot of data. We barely use them. There's one place where we use them. When we start a node, we look for the latest cut. If for some reason during shutdown, for example, we did kind of, there's some inconsistency in the database, or we lost some data, or, the node got killed and RocksDB wasn't able to flush everything to disk, which should almost not happen. They are very careful to implement it. But if there's some inconsistency in the database, so we try to load the cut. When we load the cut, we look at the cut hashes, and then we try to find the block headers for it. If that goes wrong, we go back in history and try to find a valid cut from the ones that we stored before. I'm not sure if that really is needed, but yeah, that's the only place where we use the old cuts.
If you prune all of the forks that died off and orphans and whatever, would the cuts have a total ordering?
No.
Okay.
Cuts are, and I can draw a picture after this, because you would also ask. Cuts don't have by nature a total ordering. They have a partial ordering. You can, however, we do something, you can take a subset of cuts. If you, for example, take cuts where and you can reconstruct them from the history. If you know a current cut, you can go back and construct a total order where you only keep cuts where each chain is on the same height. So I can draw a picture. Give me a second, and then it makes it easier. I just have to move my table and hope that you can see my whiteboard if I turn on my camera. So let me quickly turn around and see where I have my probably have to stop presenting. Okay, can you see my whiteboard?
Yep.
Let's see if I can get a little closer. Oh. Okay, let me know if you can't see it or I'm in the way or so. And probably have to.
No, that looks great.
Phones, I guess. Can you hear me?
Yep.
Okay, cool. Okay, so let's get a night penalty to-do list erased. Doesn't really work. Anyways, cuts essentially what our braidings. I make it top down, so history goes down. So if we have something like here, let's say we have 3 chains, and this is our initial Genesis cut. Essentially, they are braided in some way. So essentially, and let's assume it's not a graph that we would use in reality, but I think, and please stop me if I interrupt if I do something wrong, because I haven't done this in many, many months. Kind of looked into the details of this stuff. So it's somehow, let's make this, I think it looks like this. So if you assume that these chains are neighboring chains, so our chain graph would be something like this, which would be just a line of 3 nodes. Then the braiding would look like this. Of course, we wouldn't use this graph in practice, but so this would be a valid braiding.
Hey, Lars.
Yeah.
It's really difficult to see that. Is it possible to draw it bigger?
Bigger, yes, sure.
Because I know you're writing directional arrows there, which are really important.
I can also see if I find some better marker that gives brighter colors.
Yeah, that works. Perfect.
So the graph would be something like this. So this is the graph. And then a chain on top of this graph would look like this is Genesis block, so height 0. And then braiding would be, or a chain with a valid braiding would look like kind of this is the parent. So everyone kind of depends on its parent. And then everyone would have to depend on the adjacent. So these were 2 adjacent, these 2 adjacent, and it has to get the cross structure here. And actually, that's not enough. That's actually, I should, this is how we do it. But if you just have this cross structure, that's essentially what you want is if you go one step further. And that's actually the main issue that causes the deadlocks, that the braiding is not defined as a step, but it's defined as a 2-step thing. So for the braiding to be valid, and I will highlight it in a second, and this is where the whole pain in the implementation comes from. A valid braiding doesn't say, oh, you need this cross here. A valid braiding for Chainweb says you need whenever you need essentially have, when you have this dependency, you also need this dependency. And can you see the red line, or is it?
It's a little faded. That's much better.
This, and you also need. Oh well, now I have a problem because I don't have a note here. But it would also mean something like I should have started with middle one. But you also need to kind of this thing to this. Is this correct, Stuart? You have to go something like this. You need essentially this shape thing in there, and you need this triangle. So let's give it 2 different colors. So this is let's make this green. Okay, so you see the green triangle, we need this shape, and we need the purple shape, which is kind of this, how you call this in English, parallelogram?
Yeah, parallelogram.
Rhombus.
These 2 things we need. The problem is they talk about 2 steps. That's not inherently inductive. We would like to talk always about kind of a single step. So parent and now. By having 2 steps, it can be that you make something wrong here, and then you get stuck here. And then you have to go back in history and find out what went wrong here. And that can get very, very expensive.
What information do these shapes give us about the graph and the way they relate to the other nodes? Like, what are we trying to accomplish by saying, oh, look, we've got 2 shapes. And need this.
Yep. Will could probably go into a lot of detail here, Monica. So this thing actually, these 2 shapes essentially make sure that things propagate quickly. You know, that we have this good expansion properties in the graph, in the chain, that essentially from every point, if the underlying graphs are graphs with a low diameter, or generally good expansion. So if they have a low diameter, by making this braiding, it guarantees that in diameter many steps you can get from every node here to any other node in the graph.
Okay, so that's the property that we're always within, say, 2 of the next point in the node that we care about.
For example, that SPV proofs work within a certain amount, but most importantly means that security, kind of when you slide, if you slide something over, let's assume this is a long chain, you slide a window over it, kind of only look essentially, ignore everything in here, but look kind of how this node depends on something here. You kind of get a window that is diameter many steps deep, and you know that everything here depends, since it's connected to everything here, it depends on the full history of Chainweb. This means that essentially you get the same level of security that you would get in a single chain, like in Bitcoin. And this window is small; it's smaller than the confirmation depth of Bitcoin or a single chain blockchain. This means our security is at least as good as single chain security, because it means when you're at the confirmation depth, everything here depends on everything here. So essentially, an attacker would have to overcome the full hash power of the network at this point. It's not confirmation. Actually, as long as the diameter is smaller than the confirmation depth, it means essentially when you reach the confirmation depth, you already have a situation where you have kind of a total ordering kind of where everything depends on all of the history, and an attacker would have overcome all of the hash power. Does it make sense?
Yeah, that makes a ton of sense. Thank you.
Okay. And this is the property of the graph, and this structure here guarantees it. But the problem is the property is a little too weak to make it inductive, to make a distributed algorithm out of it that we can efficiently kind of define efficient merges and lattice and the things that we need.
That was my next.
Also, I would actually go so far as to say that while they're very important in the Chainweb paper, because the Chainweb paper wants to talk about security and wants to motivate having multiple chains, and also wants to prove that the parallelization that Chainweb offers is safe. Also that SPV works. That you can move assets across the chain safely. I would argue, as far as consensus goes, it's an emergent property, which is where I think you're headed. I think the inductive proof that is what kind of we use in the code is the kind of fundamental, and then the security properties emerge from that.
Okay.
Yeah. So exactly what we do in the code, and the difference is really, if you look into it into detail, it's really marginal, because if you have these two properties that end the Chainweb paper, which are essentially I'm not sure if that's proven, but probably something like the weakest precondition you have to do in order to prove all the security, everything about Chainweb. Kind of, this is essentially the thing that if you have these two things, you can prove everything you want to prove, what is in the Chainweb paper.
Right.
But in order to implement it, we essentially make a stronger assumption, which says what we really want is we want this cross here.
Right, which is your strong product.
Yeah, which is a little, it's a little stronger property, particular, but it only matters.
Also, Lars, I was just going to say, with this example, can't we make it a triangle instead of a line? And you have right now you have it as a line. If it was a triangle, then we'd have ones going off the side that wrap around.
Yeah, essentially we could copy this thing over here, and this would be now the same thing as this.
Right.
For this chain A, B, C, this would be A again.
Because then we have a consistent amount of neighbors. Like with the line, I think you have an inconsistent amount of neighbors. Yeah. And I guess Chainweb doesn't demand that everything. No, Chainweb doesn't demand that everything have the same degree. But,
no.
But it's. I think it's a little more intuitive if at least they have every node has more than one.
Yeah.
So. Anyways, I was just saying that so we get to the inductive thing, because I think that's part of the inductive thing.
Yeah.
I have a question about checking this. So do we check everything that you just stated, like the triangle and the parallelogram, when we're
no.
So the
whole point of this is that it's how to make something that, to jump ahead a little, is to how to make something that you can. Inductive means that you've basically got the block or the cut before you, and now you're one ahead. How do you validate that?
Great. Okay, that was my next.
How do you validate it without needing more history than just one? So we haven't gotten. So I'd like to hear that described.
Yeah. So one thing to you, Stuart, before is the implementation of Chainweb really doesn't care about this graph too much. Right. But if you choose the wrong graph, you wouldn't get this nice. Wouldn't get the diameter, and the security wouldn't work out. We would probably get something much larger than confirmation. You could use any graph here, and Chainweb would work. But one thing is we assume that they all have the same degree, which is just easier to implement. And I don't even know if you assume that it might work even with other graphs. Oh yeah, we have tests that use a line graph, so it would work, but the security wouldn't work. So our properties were not correct. So what we do is, Emily, is essentially one thing we noticed: if you apply these Chainweb properties, these braiding properties, and you apply it to a history, you will see that one step ahead, you always see these crosses here. So
Right.
the only difference, but what we do, we also require the crosses essentially right away, and it only makes really a difference at the first level. Kind of, you could on the head of the chain, you could build something that doesn't have these crosses nicely, and would still have valid braiding, but that would deadlock possibly. So
So
essentially what we say is we jump one step ahead and say essentially we only allow braidings that will not deadlock. For security, that's not a problem if something deadlocks, because security is a safe. Some people will know what I say now. For security is a safety property. So if the whole thing deadlocks, it's still all valid, and we can prove everything we want to prove about security, but we don't have progress anymore.
okay.
And which doesn't affect, if a chain stops, it's secure. So, but we of course don't want it to get progress and to get efficient implementations. We want this. We essentially restrict from the very beginning everything to having these process, and also this gives us the induction that we essentially you get a cut here, and I simplify now. Let's say we have this, and if you give me any node on top of it, let's say I have this cut, which is here a cut. I take another color for it. Let's make it brown. So let's say this is my cut currently, and someone says, "Oh, I mine on this cut. I find a new block. I find this block. So I put this here. I find this block, and so the new cut will be this thing. Kind of here they are the same, so they overlap. That's the important thing with cut. The next thing is it. So, we don't for the cross. We don't have this. So we don't have don't have the full crosses, but we have the beginning of the crosses. So all we need to look is assuming that this was a valid cut and had these crosses, and this is our inductive property. This thing had these crosses here. As long as I put this thing here and I check that it has the same crosses as far as is possible with these things, I know that this thing is a valid cut too. Now someone else comes and continues to mine on it, and they mine this thing. So the new cut here.
And you can automatically draw the product, and then you can verify the parallel.
And now this thing, because this node was in here, the one who mines this cut has to provide this line and this line. And we again know, since this was a valid cut, we know this thing is a valid cut too. So that's essentially, we don't have to look here, because we know essentially by having this rule that we always create these crosses, we know that we can extend these cuts. There's something in the code that is called valid cut. Colin, you remember the name probably. Valid cut extension, or is it monotonic cut extension?
Monotonic cut extension, yeah.
So monotonic cut extension, and that's that guarantees essentially, it just checks essentially these things here and gives you a valid braiding under the assumption that kind of the whole thing was constructed that way. And then
the bottom line between the sort of most recent two won't exist, right?
Sorry?
The sort of bottom line between the most recent two nodes won't exist, right?
What is this? That
one? That one exists?
Is what? Sorry?
Does that one exist?
Well, this is a cut. Kind of the brown ones are nothing that is in the code.
Okay, so it's sort of like extension.
This is my question before, and it was just because I couldn't remember. So a cut, you could think of a cut as a snapshot of the latest blocks on all chains, which therefore might be as far, like in the case of our 10-chain network, since the diameter allows for 2 block heights, you can have a cut spanning 2 block heights, but the property is that if there's only one member of any chain at any time in the latest cut. So in this one, it's at block height 2 for the first for chain A, and it's at block height 3 and 3 for chains B and C. And the other, the property I want to know is that does a cut? It seems also that a cut has to be total for chains. In other words, a cut is not a valid cut if it doesn't have every chain in it.
Yes. the code is a little lax there because when we the first version of Chainweb that we programmed, we still try to maintain it where possible, and it was no extra work. Is that the idea of having being able to not have to
Saturate.
monitor all the chains, that it only looks at the subset of the chains. So there's something in the code. Sorry.
Okay.
Yeah, so there's some parts in the code don't require that you have all the chain. For example, the cut merge algorithm, I think it works, at least parts of it, lower level parts of it work where you have cuts that don't have the same chains in there. They essentially goes and just takes intersection, kind of they prune the graph. But we currently we decided that this was not a priority because when we went over kind of our scaling models, we figured out that we can scale a lot with assuming that consensus is global and only kind of if a node wants to kind of focus on something, they can do it on the pack level. If you look at the initial picture, essentially pack and all this was per chain. There we can shard, or you could say I ignore some stuff. I don't do pack validation for everything, but we said consensus, since it only deals with block headers, which are small, should really, at least for now, look at all headers. But it would be possible to get more lenience there in the future and say, oh, we implement consensus that ignores some change. But it's get a little tricky because you have to kind of phase out. For example, to validate this, you might say, I validate only this chain, let's say B, in order to validate, and I don't care about C and A. This would mean I would still have to pull these chains in the data without validating it in order to be able to validate B fully. So essentially you would have kind of two circles, the inner circle where you do full validation and the outer circle where you just pull in the data and do partial validation. And we don't have implemented this fully. So this was, in the beginning we thought we'd do it because we had this per chain approach where every chain was expensive, having everything. Now we said, okay, we have consensus, which is lightweight, and it is on Chainweb and has all the chains, and packed we then chart and do per chain.
Right.
And
so in practice, we can say that all cuts are saturated or have all chains in them. And then as a result, the inductive thing you're talking about is that given a cut, so, and we mean in practice that a cut has a representative of every chain in it. The validation that we do happens when we add a new block to that cut. And by validating that cut's adjacent headers, as in the arrows, the crosses, when we add that and form a new cut, we inductively trust that whole cut and also all of the history before it is valid.
Yes, it's a little more complex because, so here we had a monotonic chain of cuts, which this is what this monotonic cut extension does. Here this example, we had this cut, A2, B2, C2, and the next cut was A2, B3, C2, and then the next was A2, B3, B3. So now it could be that some other node comes and it mines on this level, say another cut. Can you still see this? What I write?
Yep.
Let's say another node mines A3, B3. Let's do it on this level here. It's mines, instead of this one, it mines A3, B3, C2. So it would be essentially mining the node here and would have a cut that looked like this. So let me, I need more colors, I think. So it would be essentially a cut that goes this way.
The point is it disagrees about what the latest cut is on C. The latest block is on C.
Yeah. So we have essentially one that goes this way and the other that goes this way. So one goes this way. Is this correct? Yeah. So these are the two cuts. Now we have two cuts and they disagree. And the point is, in this case, it's relatively easy to merge. So we take them both. So now we do a merge. So in this case, it's very easy. We just...
Okay, so just to be clear, though, we're no longer talking about the inductive thing now when you do this merge.
Oh, we're still deductive in the sense that for validation, to make sure. So, but what we do is, and this is where the lattice comes into play. What we look is essentially, we look at and that's the intersection essentially. We look at the join point of these two cuts. This means we go, so assuming those are both valid cuts, there must be somewhere in the history a cut where they kind of started to split apart. Kind of the largest cut. There's the largest cut where they kind of departed.
Yep.
And this must exist because in worst case it's a Genesis cut.
In this case, it would probably be kind of the line at 2, at block height 2, or something.
Yeah. In this case, it's easy.
Or no, B3 is there, so it'd be that little V.
In this case, it's really easy because it would be this cut.
Yeah, right. B3, A2, B3, C2.
Yeah. So, because this is actually where they departed.
Quick note, everyone. This meeting is scheduled to go until 3:15. So just everyone think about the things you would like answered in this meeting, if possible, and then you can also think about things that you don't think we'll get to cover in this meeting that you would like to talk about in a future meeting, and we can maybe schedule another one. Does that sound okay? But I think we should try to respect the time frames that we have scheduled for these.
Yeah, that's fair. This might be a two-parter for me, Lars.
Yeah, well, whatever you want. So
Anyway, continue on. Just think about what you want to get in before the next 15 or 20 minutes.
Okay. See, yeah, if you want me to speed up or jump to something different or jump into the code, let me know. But okay, so for merging this is essentially we have this thing here, and what you generally do, we find this join, we go back in history. How we do it, essentially, we go. There are functions in the code that are called something like. There's several of them. Colin, do you remember the names? There's something that is just called join, I think. But essentially, you have functions.
There's meet and join.
Isn't there the word merge in there somewhere too?
Yeah, because we call it the merge two cuts, and the lattice theory behind it is not completely complete in the code. There are a few. If Emily could probably poke into it and tell us where it's not correct.
We got join, we got apply join, we got zip.
Yeah, we do the join, but in the code we use something else. It's called, the thing, Colin, when we walk the ancestors.
Oh, we were just looking at that.
Join into heavier, prioritize.
Yes.
It's part of join into heavier. Yeah, that's the
I think it's a call inside that. Yeah.
Join into heavier is not the best. It does not necessarily give the best solution, the heaviest cut, but it's done in polynomial time, and it's a relatively simple implementation. I think there is some polynomial time algorithm that kind of works always, but it's complicated. At least the one that I'm aware of. In practice, it doesn't make any difference. Our cut merges are simple, so we don't go back 1,000 things with very complex cuts and with 1,000 chains or whatever. Then it might become an issue, but. In our case, it's simple. So but essentially, there's a function that walks back history. It starts with both cuts and walks until they meet, until they agree on all chains. Kind of, they walk in parallel, blah blah blah, until they find all chains that they meet. And usually, it's just one step, so it's very very quick. And we monitor that. We have telemetry for that to make sure that nothing goes wrong there, because it could be expensive, but it's super cheap in existing chains. And then when we have this common thing. Then we take the heavier cut. So we start with the heavier one that has more weight. And then we try to, so in this case, let's say this is a heavier one. We don't know because I don't put weights on it. Let's say this is heavier, the whole cut. And then we try to add piecewise whatever we have in our pipeline for these cuts. We try to add to this cut and try to extend it as far as we can. So we essentially start with the heavier one. We put everything on the heavier. So if you walk to the place where they depart, then
heavier here means longer, like further away from the depart point?
Usually, yes, but we don't, in the chain, kind of, usually the height corresponds with the weight, but it could be that if there's an DA in the middle, there might be different.
Okay, so it's
a difficult.
It's like the sum of difficulties as you walk to.
Essentially, yeah, that's weight.
Yeah. And the weight of a cut is just the sum of all weights on all chains. And so what we do is we essentially go back in history, which is usually quick. And then we go forward and we always give preference to the heaviest cut. Because it could be in theory situations where you have to get.
But aren't they actually? So one question here is: these cuts look identical in weight. Just this in this example, you got A3, B3, and C2, and you got A2, B3, and C3.
Yeah.
So aren't they identical?
No, here we have A3 and A2, and C3 and C2. So this is the blue one, and this is the green one.
Which one's heavier?
We don't know. We don't know because we don't have weights here. Chances are that they are equal. We don't know.
They won't be equal.
Because, they won't be equal.
They won't be equal because difficulty differs just barely on all chains. So if one cut has some chains and the other one has is like say they
difficulty is like continuous.
Difficulty.
No, but it varies per chain.
Much more fine grains than height.
Yes. So if they have if they're missing some sort of intersection of chain, then despite the fact that they're sharing something, their exact height value or weight value would be different.
So that's funny. So I guess I never understood this. I never got the impression that difficulty was this kind of wild and woolly thing.
Look at the top of the block explorer, Stuart. It gives the per chain difficulties for every chain.
The difficulty is really how much hash power went in every single block, and that's not the same on each.
Right, because it's a function of the arrival time, the various arrival times, which are random, and so therefore they're going to be different on every chain. That makes sense. I just never thought that. So that's a nice property. That's a nice property for chain weight, for cut weight, then, because it means that you rarely have a tie.
Yeah, if you have a tie, it doesn't really matter. We just pick randomly one side. But it's nice to have a tiebreaker, and it's really a measure of how much hash power went into it. So we want to give preference to the hash power. But in theory, what could happen if you do the join into heavier is there could be in theory some situations where it would be an advantage to first pick the more lightweight block. Let's say if we have several steps going down, to first pick a more lightweight to make gain more weight further down, which rarely happens in practice. So joining to heavier works pretty well. We just pick the heavier one and when we go forward, we always give first preference to all the blocks from the heavier cut. And then we check if we can still sneak in some of the more lightweight cut. That's how.
And when you say sneak in, the goal here is to try to incorporate the freshest blocks, kind of, right?
Yeah, as much as possible. So we have two cuts, and we want to build the biggest cuts that we can get out of it. In this case, it's very obvious.
Well, not just biggest, but newest.
The heaviest.
Right. Heaviest. There you go. So heaviest is kind of a uniform quality thing. And when you're merging, you're trying to just get as much weight as possible.
Yeah. And generally in merging it's trivial. There's no choices here. But you can kind of in the
for this, I think the goal is sufficient just to keep moving, because the goal is to merge the two cuts so that we have the most established hash weight. So we're taking advantage of all the work that's been done. I think that would be one way to put it. Is that miners have been doing work. We've gotten two cuts that kind of conflict a little. Let's try to get the most work into what we're thinking is the best cut.
Yeah, and in a single chain, it's essentially very easy. You take whatever branch has the highest weight, and it's clear. There's only one choice if you have a single chain. In Bitcoin, you have two branches. You have two branches here. One is heavier than the other, and you pick the heavier one. Now, in our case, it could be. Now we have several chains. It could be that this is heavier than this, but this. They could disagree here. They could have two different blocks here. Here we don't have a real fork. It's not, we have two cuts, but they are completely compatible. But we could have a fork. We could have something where we have two different blocks here. Right. And we might have two different blocks here, and they might agree on this side here. And now the question is, one might be heavier on this chain, the other might be heavier on this chain. And now the question is, which one do we pick? So this example is really simple because this is not a fork. This is a perfect concurrent computation. They just are working on different parts of the concurrent computation. Essentially, these cuts are completely compatible, these two. Because there's no conflict here. You see, we can just go together and we get the result. This is A3, B3, C3. So we got everything from everything. No block got thrown away. There was no orphan here. But this is not always true. There could be orphans here. And it might be that now we have, and they agree in different ways on different chains. And now we have to make a decision. What do we integrate from what chain? And in a way that in the end, we get a valid cut again. And this is where it becomes tricky. And even defining the fork point is not trivial anymore, because they might fork on this chain on level 1, and on this chain, they might still agree on level 2, but fork on level 3 and have the first different blocks there. You see the problem there? So, and this is kind of the joint point, is essentially finding the largest cut where it's kind of some line going through where they still agree. And that's we call the fork cut. So now forking is defined across all chains. The fork cut might be somewhere here, and then we go from there, and then we try to construct a new cut that is as good as we can. But it's not our algorithm does not guarantee that it's optimal. But in practice, it is.